Team PChem, and welcome to lecture, where today we're going to start a new unit with a focus on spectroscopy. Before we get into some of today's course content, I think it's good for us to actually take a moment to step back and think a little bit about the big picture of where we've been in the course thus far and where we're going for the remaining third of the semester. As chemists, our overarching goal is to be able to understand the properties of small systems, normally on the atomic scale. And I hope that you've seen through this course that there's a number of applications that chemists might care about where physical chemistry can lend some insight. Examples of these applications that you've seen so far in class are how the behavior of quantum dots works. In our MO unit, we talked a lot about bonding and reactivity, as well as the magnetic behavior of molecules. And coming up later in this last third of the semester, we're going to talk about spectroscopy. The big question for all chemists is, how is it that I make a connection between principles of physics and principles in chemistry to the underlying behavior of the molecular system so that I can really focus on the applications that I care about, being able to predict and interpret why these systems are behaving the way they are to give chemists and other folks working on practical applications some insight into the problem. And so our job as physical chemists has been to make these connections between knowledge of what the structure of the system looks like and knowledge of what the properties of the system will be. In order to do this, I would argue that we have had two major axioms in this course that have guided us through to this point. The first axiom is that the properties of a system can only be understood by understanding the potential and kinetic energy of that system. So what do I mean by this? I mean that in the different systems that we've studied thus far in this course, our first step in trying to solve for the wave function and the resulting energies has been to define what the potential looks like. We've seen many different example potentials in this course, starting off with a particle in a box, moving on to, for example, the hydrogen atom, and I've chosen to show the hydrogen on this atom on this slide as an example of electronic motion. What's the relative motion of an electron with respect to a nucleus? Well, that one, in this case, the potential is given by Coulomb's law. Q1 times Q2 divided by R. Other examples of different types of motion of the system also exist, but are not ones that we've typically explored thus far in the course. Where we're going to go for the next third of the semester is trying to understand what vibrational motion looks like, along with rotational motion. And then last but not least, we've talked briefly about translational motion via the particle in a box model, although that connection hasn't been yet made explicit. So we've seen these different types of motion, and each correspond to a different type of potential. How does that help us, though? It turns out that once we understand the relevant motion of a system, we can then use axiom 2 to help us out. Our second axiom for this PChem course has been that the wave function and relevant energies of a system can be solved for using Schrodinger's equation once we know what the relevant potential energy is that describes the motion of the system. And so for the different types of motion that we've explored in this course, translational motion being one, again, we haven't made the connection explicit, but it turns out translational motion is the particle in a box model. We can take a model of that system, solve for the wave function, and as we explored in one of the case studies at the beginning of the semester, once we have those wave functions and corresponding energies, we can solve for how a particle in a box, something like a quantum dot, is going to behave with respect to the emission and the absorption of light. We went on a similar journey when we went to talk about the electronic energies of a system. So this was our model for the hydrogen atom, where the potential was cast in terms of Coulomb's law. Not only did we study the hydrogen atom in this case, but we also used more approximate theories, MO theory, and that linear combination of atomic orbitals to help understand how this model potential could help us understand molecules. And if you wanted to go beyond MO theory, we briefly touched on some advanced theories that you can use in computational chemistry to help you understand the problem. And once again, once we had these wave functions and corresponding energies, there was a lot of rich chemistry that we could do to try and understand applications in bonding and reactivity, as well as we were able to correct some of the misconceptions of Lewis theory and correctly predict the magnetic behavior of molecules like O2 and N2. Two other types of motion that we're going to study in the remaining third of this course, one is vibration. This is going to be the motion of two atoms, the nuclear motion with respect to one another. And what you're going to see in today's lecture is that that vibrational motion can be described by a quadratic potential. A second type of motion that we will explore by the end of the semester is rotational motion. How is it that two atoms can rotate with respect to one another? I haven't listed the potential energy yet on this slide because I do want to focus either on expressions for the potential energy that we've seen so far or that we're going to touch on later today. And so for the remainder of this course, the theories and models that we're going to use to talk about vibration and rotation are first, for vibration, the harmonic oscillator model. And we're going to directly connect the results of this model to spectroscopy so that we can see the connection between experimental results that we can measure in the lab and the theory results that we would predict using the harmonic oscillator model. As for rotation, we'll develop a second type of model called the rigid rotor. And this rigid rotor model will also help us understand certain spectroscopic results, which is going to be really useful for us in this course. And so I'm going to pause here and give you a moment to kind of look over and reflect on this slide. The main takeaway that I want us to see is that our workflow in physical chemistry is always the same workflow. We may have different potentials of the system that we seek to describe, depending on if we're talking about electronic motion, translational motion, rotational, or vibrational. But in all cases, we have to start by coming up with an appropriate theory or model for how we should think about that potential for a chemical system. We then have to solve Schrodinger's equation, and only then can we use the results from physical chemistry to better help us understand the properties of molecular systems. And for our last third of the course, we're going to really start focusing on spectroscopy as our application area of interest. And in particular, while spectroscopy is really broad and far-reaching, I've chosen to give us a case study in astrochemistry, which is the part of chemistry that focuses on the molecules that appear in interstellar space and how we can know what molecules are present under different conditions. It's pretty exciting. It's a lot about kind of origins of life and how we can measure things even when we're not physically close to them in the lab. And so I hope you enjoy that part of our application side of the course. All right. And so with that, let's go ahead and start talking through our lecture for today. I have a couple of goals for us today in this lecture. The first goal is going to be to start talking about molecular vibration. And I want to show you by the end of today's lecture how it is that we can model the molecular vibration of a system using what's called a harmonic oscillator model. And that's going to help us keep track of bond stretches and compressions, and we'll get to see how even those two motions of the system end up being quantum mechanical. Once we have our model in place, we're going to solve Schrodinger's equation for the harmonic oscillator and then analyze the resulting wave functions and energies. So this process is going to be pretty similar to how we tackled something like the particle in a box. The math is just going to be a little bit different. The resulting wave functions and energies will also be different. And then last but not least, I'm going to give us a brief example of how, if we understand the transitions that occur between energy levels for the harmonic oscillator, that we can understand and glean some information about the chemistry of the system. And in particular, these energy transitions are going to help give us information about bond strengths. And so with that, let's get started. Now, before we really get going today, it's worth doing a brief physics review on a model system that you would have looked at in classical mechanics. And that model is a ball and a spring type model. So I've shown a picture of it towards the right side of the screen. A ball in a spring model is going to take a ball of a certain mass. For reasons that will become apparent later, I'm going to call that mass mu, using the Greek letter that kind of looks like a fancy U. And we're going to connect that spring to a wall. So the wall is not going to be allowed to move. So I'm going to maybe put that wall in orange. Our wall is not going to be allowed to move, but the mass in the spring will be. Now, the simplest model for how this spring behaves is what's known as Hooke's law. Hooke's law tells us that the force exerted on the ball is equal to -1 times something called the spring constant. It's going to be a parameter that measures the stiffness of the spring. And then also, our force is going to be dependent on x, which represents the displacement of this particle away from its equilibrium position, x equals 0. So why does this force make sense? Well, you may notice that if I try and take my mass, here's my equilibrium bond position. If I try and take this mass and pull it to the right, Hooke's law tells me that there should be a force moving us in the negative x direction, back towards equilibrium. That is what's called a restoring force. Similarly, if starting in my equilibrium position, I take my mass and I try and displace it towards the left, that in this case would mean that I'm compressing the spring. Then now, because I have a negative value of x, my force is going to push me to the right, and again, push me back towards equilibrium. So, since in general, force is equal to the negative derivative of the potential energy with respect to position, we can solve for what the potential energy would be for a spring that's subject to Hooke's law. In that case, after I do a bit of integration, I discover that the potential energy is quadratic in nature. It's equal to 1/2 times k, our spring constant, times x squared. And that means that now that we have a potential for this system, I can go ahead and set up the time-independent Schrodinger equation. Remember from earlier lectures that our time-independent Schrodinger equation in one dimension is h hat, the Hamiltonian, times psi is equal to E psi, where our Hamiltonian operator is a sum of the kinetic and potential energy operators, which in turn means that the form of the Hamiltonian is negative h bar squared divided by 2m times the second derivative of the wave function with respect to the position, plus a term that describes the potential energy. So now that I have that defined for my spring, that means that my form of the time-independent Schrodinger equation is shown in blue. And it turned out that the math for going through this solution has been done before, but is somewhat complicated relative to the amount of information that we can glean from it. So I'm going to go ahead and throw you all a bone and simply present to you what the results are for solutions to the time-independent Schrodinger equation for this problem. And they turn out to be equal to n, a normalization constant, pretty standard, times a function called h, where h is something called a Hermite polynomial. We'll get to that in a second. And then last but not least, our wave function also has a component to it that is a decaying Gaussian function. So that's that e to the negative ax squared divided by 2. So let's unpack a couple of the terms that show up here. One thing I want you to notice is that for these solutions, perhaps unsurprisingly at this point in the course, we wind up with a quantum number. That quantum number we're going to indicate using the Greek letter nu. It kind of looks like a fancy V, and you can think about it as the vibrational quantum number. The restrictions on nu is that nu has to be an integer. 0 is perfectly fine, so nu can take on values 0, 1, 2, all of these are allowed. The second thing I want you to notice is that these Hermite polynomials are, while something that you haven't seen before, they're a special set of functions, they're actually fairly straightforward. You'll notice that as our value increases, as shown in the chart at right, that all of these are just polynomials. And so for nu equals 0, the Hermite function is just 1. if we go up in order, the leading order term in the polynomial corresponds to the quantum number. And so these different graphs have, if you like, different amounts of oscillations that appear in the Hermite polynomial. And in fact, there's a direct relationship between nu, the quantum number, and the number of nodes that are present in this Hermite polynomial. And so since the wave function is the Hermite polynomial times the decaying Gaussian, that means that the overall shape of the wave function is going to be oscillatory, but at large displacements, it's going to damp out, and that's because our decaying Gaussian function is eventually going to make sure that the wave function goes to zero in the limit of large displacements. And so if I were to plot these wave functions, they would look as follows. Here on this graph, I've shown for a variety of different displacements shown on the x-axis, and then different wave functions that are just spaced out so for visual clarity. On the y-axis, I've shown the first 7 different solutions to these wave functions. The oscillatory behavior, again, these squiggles, is coming from the Hermite polynomials, and the damped out behavior at large displacements is coming from the Gaussian portion. And so I want you to notice 2 different important features of these wave functions. The first thing I want us to notice is that, just like in the Hermite polynomial case, the number of nodes present in these wave functions is exactly equal to the quantum number nu. The second fun fact that I want us to notice is that at nu equals 0, we see, based on the shape of the wave function, that the particle is most likely to be found at x equals 0. However, for larger values of the quantum number, so for vibrationally excited states, nu becomes increasingly, as nu becomes large, it becomes increasingly more likely to find the particle towards larger and larger displacements. And so my wave function for example, psi 7, which is shown in green, has a lot more probability density for the particle to be found at rather large displacements, especially if you compare it to psi 0. Last but not least, each of our wave functions in this mass on a spring has a corresponding energy expression that's really pretty simple. It's given by the expression E sub nu equals nu plus 1/2 times h bar times the square root of k, our spring constant, divided by mu, where mu represents the mass of this mass on a spring. Here too, with this energy expression, I think there's 2 important points to highlight for us. The first important point is that the lowest energy of the system, the ground state, where nu is equal to 0, has a non-zero energy. So this tells us that if the energy is non-zero and the potential energy is sort of positive everywhere, again, 1/2 kx squared, so our lowest value of the potential energy is 0, that must mean that regardless of what quantum number we have, the kinetic energy of the system has to be positive and can never be 0. That means that our quantum particle, that's a mass on a spring, can never be at rest. And that kind of makes sense in light of the Heisenberg uncertainty principle that we learned about towards the beginning of the semester. This ground state energy is sometimes called the 0-point energy of the system to help us remember that, unlike the harmonic oscillator in a classical situation where the particle can be at rest, our quantum particle always has a little bit of energy even in its lowest energy ground state. The second point that's worth noting is that in this mass on a spring example, the energy spacing between successive energy levels remains constant. Delta E is equal to, for a gap between successive energy levels, E of nu plus 1 minus E of nu. If I plug those values into my energy expression and do a little bit of simplifying, I wind up with delta E equals h bar times the square root of k divided by mu. And why this is so interesting is that in this model, the energy transitions in the system are going to give rise to either an absorption or an emission of a photon whose wavelength depends very directly on the mass of the particle and on the stiffness of the spring, which was our spring constant K. So that's really nice for us. It's a fairly abstract physics example, and it would be great if we could then bring this to a more chemistry-related connection. So let's talk about how this math on a spring problem can be related to studying molecular vibration in diatomic molecules. So to get us started with this, let's consider a diatomic molecule. I'm going to use carbon monoxide just for example purposes. At small displacements, or assuming that we're not too far away from our equilibrium bond distance, it turns out to be reasonable to model the two atoms as being connected by a spring and subject to this Hooke's law force, or this harmonic oscillator potential, if you like. Very similar to our mass on a spring example, the two model parameters that we're going to introduce are, first of all, R sub E, the equilibrium bond distance of this molecule, and secondly, K, the spring constant. In this case, K has a very nice chemical interpretation, which is that it represents the bond strength of this diatomic molecule. A larger value of K means a stiffer spring, harder to move these two atoms back and forth, corresponding to a stronger bond, or if K is small, it means it's relatively easy to move these two atoms apart, which chemically corresponds to a weaker bond. The potential energy for this system, where I have my diatomic molecule composed of two atoms connected by a spring, looks very similar to above. The only thing we need to do is, instead of kx squared, now we need to explicitly talk about that displacement as r, the current bond length, minus re, the equilibrium bond length. And so our expression for this internuclear distance being able to change for the diatomic molecule is V of r equals 1/2 k times the quantity r minus re squared. The second little change that we need to make is that the mass of the system from above, where we had a mass connected to a spring, connected to an immovable wall, has to be modified somewhat to account for the fact that both the carbon atom and the oxygen atom are allowed to move. The replacement that we make is that the mass from above translates into what's called the reduced mass. Mu is equal to m1 times m2 divided by m1 plus m2. And in this case, for my example with carbon monoxide, m1 would be the mass of a single carbon atom, m2 would be the mass of a single oxygen atom. We're going to use a special name for this potential called the harmonic oscillator. And this one is very popular in the literature because, as we'll see over the next couple of lectures, it's a very useful model for trying to understand how molecular vibration leads to energy transitions that can be observed using IR spectroscopy. Notably, the wave functions and energies associated with this model are near identical to those described for mass on a spring. And so I've reproduced both of these expressions on this part of the slide so that you can see these, write them down, make sure that you have these available, because we'll need both a description of the wave function and of the energies to really understand the properties of this diatomic molecule being able to undergo bond stretches and bond compressions. So once again, our energy expression in particular I want to highlight is equal to that vibrational quantum number plus 1/2 times h bar, Planck's constant divided by 2 pi, times the square root of k, which is our spring constant, but also represents or is correlated with our bond strength, divided by mu, our reduced mass. And so how I want to end this for today is to go through one practical example of how this harmonic oscillator model can be used to understand energy transitions in a system, as well as glean a little bit of information about bond strength. So the example problem we're going to go through to end up today's lecture is that we're going to study an energy transition from mu equals 1 to mu equals 0 for both a typical CC double bond as well as a CC triple bond. And the information that I'll give you for this problem that I got from an IR spectra but which will take another lecture or two to be able to understand for ourselves as a class how we get these wavelengths. I saw from an IR spectrum that when a CC double bond undergoes this energy transition, it emits a photon with wavelength psi 1, where the one subscript I'm going to use just to help me with the double bond, that is equal to 6 times 10 to the negative 6 meters for my wavelength. Whereas for a triple bond, the wavelength is a little bit smaller, 4.5 times 10 to the negative 6 meters. And what I'd like us to do for this problem is, assuming both bonds can be modeled as harmonic oscillators, I want us to calculate the spring constants K1 and K2 that are associated with these two different types of generic bonds, and then chemically interpret the results. Okay, so if you'd like to try and work on this problem by yourself, I would recommend pausing the video at this point and seeing if you can work through the problem yourself. Otherwise, I'll go through it step by step in just a moment. So our first step of this problem is going to be to calculate delta E, that energy transition. And this is going to use information that we've already gone over when we were talking about the particle in a box. If I have a photon of a certain wavelength, the energy of the photon is given by h, Planck's constant, times c, the speed of light, divided by the wavelength of light that was emitted. And because those energy transitions have to emit a photon that is exactly equal to the magnitude of the energy gap, that means that delta E is also equal to hc over lambda. And so I've shown explicitly how I've gone about this for my first wavelength of interest. We get a result of 3.3 times 10 to the negative 20th joules. Hopefully we can see that compared to when we were talking about the hydrogen atom, where our typical energy transitions were on the order of 10 to the negative 18 joules, these energy gaps are quite a bit smaller by a factor of about 100. For the second energy transition, I've not gone through the math in explicit detail, but I encourage you to check with your calculator and make sure you can get the same answer that I do. Now that we've calculated delta E, a second step that we'll need to do before we can relate this to the bond spring constant is we need to calculate our reduced mass mu. Remember that mu is equal to m1 times m2 divided by m1 plus m2. And in this case, both of our masses are carbon atoms, regardless of whether you're talking about a double bond or a triple bond. And so to calculate the mass of a single carbon atom, we can look up the molecular weight from the periodic table and convert that from grams to kilograms so that we're all consistently in SI units, and then divide by Avogadro's number to give us the mass of a single carbon atom. And that mass is on the order of 10 to the negative 26 kilograms. Plugging this result for the mass of a single carbon into our formula for mu, we wind up with mu equals 9.97 times 10 to the negative 27 kilograms. And then last but not least, we're going to go ahead and solve for K. So we know from our harmonic oscillator model that delta E is equal to E of V1 minus E of V0. And since all of those transitions are the same energy gap, delta E does not depend on the successive energy levels that we're talking about. We saw earlier in today's lecture that delta E is simply equal to Planck's constant times the square root of K, our spring constant, or our bond constant as it's sometimes referred to, divided by mu. Solving for K, that lets us know that K is equal to delta E times h bar squared times mu. We've already solved for delta E, we know Planck's constant, and we solved for mu, and so we simply have to plug in those values to get our final answer. And what we obtain is K1 equals 984 newtons per meter. The units come about from doing a systematic unit analysis of delta E in joules, Planck's constant in joules per, I deleted my divide by sign. Sorry, it should be delta E divided by h bar squared times mu. So h bar is in units of joules times second, and mu is in units of kilograms. So that gives us an overall unit of newtons, a measure of force, divided by meters, the distance. And we see that K2 has a slightly larger value compared to K1. In other words, the bond constant for a triple carbon bond is larger than that for a double carbon bond. And this should make sense to us because we learned in general chemistry that a triple bond is a stronger bond compared to a double bond. And using this calculation based off of some experimental results, we can compare just how much stronger that type of bond is. All right, and so that's pretty much it for today. I want to wrap up by giving some takeaways from today's lecture, namely that we saw in today's lecture how we can model a diatomic molecule as a harmonic oscillator and with two model parameters, R sub E representing our equilibrium bond length and K representing our spring constant, or sort of a measure of the stiffness of this bond or of its bond strength. The second takeaway is that by solving the time-independent Schrodinger equation, we were able to derive, or in this case mostly state, the wave functions and energies associated with the model. The energies and wave functions have a single quantum number associated with them, nu, and in all cases, our wave function exhibits this oscillatory behavior that damps out at large displacements, but still allows the particle to move from small displacements to fairly large displacements. Similarly, our energy expression can be used to show that the transitions between energy levels for the harmonic oscillator are all the same, h bar times the square root of k over mu, and that can help us, in collaboration with experimental results, start to see how we can use spectroscopy to predict chemical information like bond strengths. So that's it for today. Where we're going to go in the future, in the next couple of lectures, is we're going to talk about exactly how this harmonic oscillator model is more directly related to experimental results. And we're going to do a deep dive into IR spectroscopy, both so that we can understand the technique itself, what results we would expect to see in terms of photons that are absorbed or emitted, and then last but not least, so that we can continue to connect the results from quantum theories to experimental results so as to derive and learn more chemical information about a system. So that's all I've got for us for today. I look forward to seeing you all in lecture. Take care.